Because who knows, maybe someone just luckily guessed at it. All right. So whenever we're doing double angles, I have to find cosine 2 alpha or cosine 2x first. Well, they gave me cosine 2 alpha, so we skipped that whole first step of finding it because we already have it. And we can just plug this straight into either this equation that I had you guys write down, or you can write it into, or plug it into any one of those cosine 2x formulas. Probably not the one with the square root or the cosine squared, sine squared, because that wouldn't work. But the other two, you could plug it in for and solve. But you can see I plugged the 3 over 5 in. I always use 5 over 5 so I don't have to keep change flip. I came up with a square root of 8 over 10, which simplifies to 2 square root of 5 over 5, which is positive because we're in quadrant 1 with alpha. If 2 alpha is in quadrant 1, alpha must be in quadrant 1, but I did show the math also. I just divided everything by 2 to say that alpha must be between 0 and 45. Once you know cosine, you can get sine really easily. Either you can plug it in here, or you can use the fact that cosine 2 alpha equals 1 minus 2 sine squared, and you can plug the cosine 2 alpha. All right, questions from the homework? Number 6. Do you have a number 6, 7? 6. All right, 6 or 7?
7. 6.
We'll start with 6 because it's first. So 6 says, prove this identity that tangent squared equals 1 minus cosine 2 alpha, or theta, over 1 plus 2 cosine 2 theta. So I start on the right-hand side and say I need to rewrite cosine 2 theta as something. But we have 3 options to rewrite cosine 2 theta. So what I normally do is I look at the left-hand side to tell myself which one of those 3 to pick. It's tangent squared on that side. That doesn't necessarily help me. Maybe if you can picture what tangent squared can be rewritten as, you can. But I'm going to go ahead and rewrite tangent squared as just sine squared theta over cosine squared theta. Well, now I'm going to circle sine squared because that has something to do with my cosine 2 alpha. That tells me I need to rewrite cosine 2 alpha, and the one of the 3 I'm going to pick is the one that just has sine squared in it. Because I don't want cosine squared on top, so I'm going to pick the one that just has sine squared in it. So that's become 1 minus 1 minus 2 times sine squared theta. All right, my bottom cosine 2 alpha. I need to rewrite that as well, and I need to rewrite it as one that just has cosine squared in it. So I'll take a picture of the finished answer so I'm not writing it all down. So once again, I picked 1 minus 2 sine squared to rewrite cosine 2 alpha on top. I picked 2 cosine squared, I guess I changed it to x on that side, minus 1 on the bottom one. You simplify, and you're going to find out you just get to sine squared over cosine squared, and you're done. All right, and 7, you said?
Yes, sir.
Any questions on this one? Does that make sense? 7 is very close. 7 says cosine 3x equals cosine x 1 minus 4 sine squared x. So I'm looking at cosine 3x, and that's a triple angle because it's 3 times an angle. I don't have a triple angle formula, so I need to rewrite it as a double angle formula. The easiest way to do that is just rewrite it as cosine of 2x plus x. Let me put a line through here. Well, that's going to give me, because I'm going to use my sum angle identity. You can write that on your sheets if you want. You can write your sum angle identities. But cosine of alpha plus beta is cosine times cosine minus sine times sine. So in this case, cosine of our first angle, so we'll have cosine of our first angle, which would be 2x, times cosine of my second angle, which is x, minus sine of my first angle, which is 2x, times sine of my second angle, which is x. So now, the only two I need to rewrite are sine of 2x and our cosine of 2x. Well, sine of 2x is pretty easy, because the only way to rewrite that double angle is 2 times sine x cosine x. So I got that down. The only one I have to think about is cosine 2x. Like I said, these are the only things that's the gum in the works of these, is because there's 3 possible ways to rewrite it. It's our cosine squared minus sine squared, our 1 minus 2 sine squared x, or 2 cosine squared minus 1. Well, what's going to tell me what to do is my right-hand side. And more particular, I'm looking out for squares, cubes, quadrant, anything that's bigger than the power of 1. So I'm going to immediately notice that I have 4 sine squareds. Do we have any cosine squareds on the right-hand side? There are no cosine squareds on the right side. So immediately not having cosine squareds pretty much guarantees me I'm going to pick the one that doesn't have any cosine squareds in it. And I'm going to pick the only one that just has sine squared, and that would be our 1 minus 2 sine squared. So let me take a picture of, so that was the big step we had to do. And that's exactly what I did in my notes. I said, hey, rewrite this as 1 minus 2 sine squared x. Simplify, simplify, and you'd come down to your same as the other side. All right, questions on that? Does that make sense?
Yeah.
Okay, other questions? Other questions going once? Twice? Is it 3 times? 4 times? 5 times? Okay, if there's no other questions, then we'll roll right into today's lesson. Today's lesson is not super brain heavy taxing formulas. It is pretty straightforward. Either you know how to do it or you don't. Either you practice it or you don't. So we have up there, it says find all real solutions such that, what do I have? Cosine x equals square root of 2 over 2. This is kind of like our inverse problems. In fact, you could see this as an inverse problem, because if I would take the inverse of cosine here, my cosines would cancel out. Let me just show that real quick. We're not going to actually do that, but you can kind of see how that would work. We would do cosine inverse of that side, which would cancel that out. I do the cosine inverse of that side. And this, in fact, would be a problem that x equals the inverse of the square root of 2 over 2, but that isn't the problem we're doing at hand. Instead, this wants every possible value that I plug in for x that will result in square root of 2 over 2. If you go ahead and you look at your unit circle, and we will have to look at our unit circle or just know it, we're going to look where cosine equals a positive square root of 2 over 2. And cosine equals a positive square root of 2 over 2 at 45 degrees and at 315 degrees. And that means on that little unit circle that I gave you, you would mark it here. That's our 45 degrees. And down here, which is our 315 degrees. So those are our two solutions that are on the unit circle. However, did I say pick the values that are on the unit circle? No, I said all real solutions. So let's start with 45 degrees. If I would add 360 degrees to 45 degrees, I would end up at the exact same place with the exact same solution. So for this one right here, for that angle right there, these are all the possible solutions that work for this one. It would be 45 degrees works. 45 degrees plus 360 degrees would work. Well, that's 405. So we could say, well, 405 plus 360 degrees works, plus 360, plus 360, plus 360. And that's not even all my solutions, because I can keep adding 360. Not to mention, I can subtract 360 over and over and over. Now, we don't have time, because it would take an infinite amount of time, to actually list all of our possible answers by adding 360. So we're going to use something called set builder notation to represent every one of these possible values. And this is how set builder notation works if we don't remember. Well, we're going to put a brace. All right, we're just going to have a brace, and we're going to put an X at it. What this is saying with a brace and an X is it's saying all values of X. This right here says all values of X. And then we're going to put a vertical line. That vertical line stands for such that. So this is saying all values of X such that, and now we're going to put an equation that stands for X. And it'll be such that X equals your very first angle, which is 45 degrees. And we know that I can add or subtract 360 degrees from it and get the same solution. So we're going to say plus 360. And we're going to multiply that by K. Now you might ask, why am I using K specifically? And it's to pretty much shortcut this. So don't write what I'm writing, I'm just showing you why I picked K. So normally with set builder notation, you would have to put K, and you might have to put something like, let's just put such that. We'll put K is an integer. All right, so normally you'd have to put that in set builder notation. However, the fact that I picked K will allow us to just end at K. Because with set builder notation, it's pretty much assumed that K is automatically an integer. All right, so we don't have to put that extra stuff on there. Nor do I think all of us are strong enough to do set builder notation that we want to have to add that such that K is an integer on every one of these problems. All right, so we're just going to use K, and we're all going to know that K is an integer. So this means 45 plus 360. 45 plus 360 times 2, or 720. Or it could be 45 plus 360 times a negative 1, in other words, minus. So these are all the possible solutions using this angle. Now we have to talk about the second angle, because the second angle is also solutions. So we're going to go ahead and put an OR. And we're going to say OR X such that X equals that angle, which is 315 degrees, plus 360 times K. So in short, all I'm doing is listing the possible angle that's the solution and all of the coterminal angles to that same spot. And now I listed every possible answer that if I plugged it in here, we'd have the correct answer. Those are all of them. All right, any questions on that? If you feel very, very comfortable at set builder notation, you can combine these two things together to write X such that X equals 45 degrees plus 360 times K, or 315 degrees plus 360 degrees K. If you feel super comfortable with it. Otherwise, I would personally just stick with this, because then I know I did everything correct. All right, rather than trying to push them together. So I would stick with this answer here. I'll actually give all my answers in that. On the answer key, I believe I put them all like that as well. I just like this for people that are just learning this, that you can see it's two different angles being added to 360. But if you've done set builder a lot and you're just like, well, that's easier, by all means. But this is where I'm going to do my solutions. This is what I'm going to teach it as. Okay, the next one says, find all real numbers that satisfy this equation. Sine of x equals negative 1/2. Once again, we're just going to go to our unit circle and figure out where sine equals negative 1/2. Well, it equals negative 1/2 here, and here. So I'm going to use radians for this one. So I'm going to use 7 pi over 6 and 11 pi over 6. So I'm going to go ahead and first mark it on here, just so it's in our notes. So it's here, that is 7 pi over 6. And here, which is 11 pi over 6. So now to list all of my possible ones, we're going to use set builder notation again. So I'm just going to use a brace. X such that x equals that first angle, which is 7 pi over 6. Plus, this is one of those weird notation ones. What's 360 degrees in radians? 2 pi. It's 2 pi. So it would make perfect sense to write this as 2 pi k, right? And I'll be 100% honest, I'll accept that. That's 100% correct. The more traditional way, and don't ask me why, it's just the way it is. The more traditional way to write this is 2k pi. If you write 2 pi k and it makes more sense you write it that way, by all means write it that way. I'm just going to say on my answer key I have it as 2k pi. I just want to show you why I have it in that order. All right, and it's more traditional. If you look in our textbook, I bet you anyone is going to have 2k pi instead of 2 pi k as well. All right, so that's that first angle. Or let's go ahead and list the second angle. So that's x such that x equals 11 pi over 6 plus 2k pi. And that's our complete answer for that one. We're done with that one. All right, on the next page, I want you to do the first 3. I want you to do the first 3. You can work together. I'm just not going to do them right now. I'll show you the answers. So you're in charge of these 2, and then the left one. So sine of x equals 1. Let me tell you how I want to do them. The first one, degrees, radians, whichever one you want. Once again, degrees, radians, whichever one you want. The first one, here's what I got for the first 2. Cosine equals -1 only in one location, that's 180 degrees. So I just need one set builder notation. I just build it up on this circle going around and around and around. So it's 180 plus 360 times k. For sine x equals square root of 3 over 2, there's 2 possible answers. There's one at pi over 3, there's one at 2 pi over 3. So I did have to create 2 set builders that gave me x equals pi over 3 plus 2k pi, or x equals 2 pi over 3 plus 2k pi. All right. Oh, I'm sorry. I'm going to go too fast. All right, for sine of x equals 1, there's only one location that equals 1. And since it's my y value, it's way up here. I'm going to go ahead and use 90 degrees. So I'm going to do the set builder notation. Hey, any value x such that x equals 90 degrees plus 360 degrees. That's not a 0, that's a 0 times k. All right, I think we're fully capable of doing tangent x equals 1. That's not why I had to stop there. It's because tangent values are just a little bit different. We can simplify the process just a little bit. So if you look where tangent x equals 1, it equals 1 at 45 degrees and also at 225 degrees. Now here's the cool thing about tangent ones. If you look really quick, if I go all the way around the circle to the next one, that is plus 180 degrees. And if I go from here to here, that's also plus 180 degrees. So if our 2 points are exactly 180 degrees or pi units apart, we just have to write one set builder notation. And that is write our x such that x equals our first angle, 45 degrees, plus, and instead of 360, we're just going to do 180. Okay, because that covers all of them. If I add 180 to it, I get here. If I subtract 180, I get here. I cover all of my bases with tangent, or if they're directly across from each other, we can just use 180 instead of 360. So that's going to work with most of our tangent values, because tangent are positive and negative across from each other. This will also occur on very specific sine and tangent values. Look where cosine and sine values. Look where our cosine equals 0. It equals it up here and right down here. So that one you could use the plus 180. Just like where sine equals 0. We can use 180 to get from each one of those. So in short, we can use the 180 for most values of tangent, and when sine equals 0 and when cosine equals 0. That's the time when we use our 180 or pi times k. Alright, so that's why I held off on that one, just because you can write it a little bit different. The very last one is find the cosine of x equals 2. What's the biggest value of cosine on our unit circle?
1.
1. What's the smallest value?
0.
Negative 1. Cosine can be any value between negative 1 and a positive 1. If it falls outside that range, so it says, where's cosine equal to 2? Well, cosine equaling 2 would be way out here. Maybe I should do that in red. Because that would be the point 2, 0. That's off the unit circle. So there are, in fact, no solutions. In other words, negative 1, cosine has to be somewhere between negative 1 and a positive 1 for us to have a solution. Same thing with sine. So if it's ever too big, we just need to put no solutions. Basically, if you can't find it on the unit circle, there's no solutions. All right. Your homework is ridiculously kind of short. I shortened it a little bit because I figured too many of these. If you do 8 of them, you pretty much know how to do it, so it isn't 1 through 29 like it says on top. Yes?
Do you have to do it in degrees and radians?
Yes, that's what the directions say, yeah. So I took out a whole bunch of problems, but I added the fact that I'm not going to let you choose. You have to do each one in degrees and radians. So basically you come up with your solution, and then just convert everything to degrees or radians. It's not that bad. You still have time to work on it. Most of you would probably be pretty close to done, if not done by the end of class. It's not earth-shattering stuff.